Hello, and welcome to Maths with El Profe Lo. I'm doing some elementary number theory, and in this video we'll be investigating divisibility. We used this exact same problem to investigate the Chinese remainder theorem in a previous video, but here we're going to use and solve this particular problem using divisibility. Okay, and so we know about the Indian mathematician Brahmagupta, and you can read more about him or watch more about him on the links that I provide, and poses the following puzzle. When eggs in a basket are removed 2, 3, 4, 5, or 6 at a time, there remain respectively 1, 2, 3, 4, or 5 eggs. When they are taken out 7 at a time, none are left over. Find the smallest number of eggs that could have been contained in the basket. Okay. Well, let's get to the information on how we can use divisibility to determine the solution. Okay. So, we know that none are left over if I am taking 7 at a time. Okay. So, I do know that 7 is going to divide my number, and I'll just call it k, okay, where k is going to be some integer. Okay, now, in fact, for all our piece, we're going to have these be integers, right? Now, it's going to be important that if we look at this, right, then when I take in groups of 2, I have 1 left over. In groups of 3, 2 left over. In groups of 4, 3 left over. In groups of 5, 4 left over. And in groups of 6, 5 left over. So in other words, I am actually short one particular, right? I am, in fact, short by 1 to complete a set if I'm taking in 2s, 3s, 4s, 5s, or 6s. So how could we write this out? Okay, well, I could say that k would have to be equal to 2a minus 1, right, where a is going to be some integer, but k would also have to be equal to 3b minus 1, where b is some integer. And technically we want these to be positive, so we're going to go ahead and put these up here to be positive. All right, we also know that k needs to be equal to 4c minus 1, where c is a positive integer, and k needs to be equal to 5d minus 1, where d is a positive integer. Okay, and then of course the last one that we would have is k would have to be equal to 6e minus 1, where e is some positive integer. And that's because of what we have here, right? That if I am short 1 from 2, short 1 from 3, short 1 from 4, I can write that in this form. So 7 divides k, right? So I could say that k is going to be equal to 7f, where f is some positive integer. Okay. Now, what does this tell me? This tells me that k is equal to 7f, but is also equal to 2a minus 1, which is equal to 3b minus 1, which is equal to 4c minus 1, which is equal to 5d minus 1, which is equal to 6e minus 1. Okay. Well, check the following out. K plus 1, therefore, would have to be 7f plus 1, which would have to be 2a, which would have to be 3b, which would have to be 4c, which would have to be 5d, which would have to be 6e. Right? That if I added one more egg, I could do groups of 2, groups of 3, groups of 4, groups of 5, and groups of 6, and I would have 1 left over if I was in groups of 7. All right, so k plus 1, right, would satisfy this. Okay, now what would be my next step? What do I notice? I notice that the least common multiple of 2, 3, 4, 5, and 6, that least common multiple is going to be given by 60, right? Now, what's a way that I could do it? Well, I have 2, I have 3, I have 2 squared, I have 5, and I have 3 times 2. Okay, so my least common multiple is going to be given by taking my highest powers of my prime factorizations of each of my numbers and multiply them together. So 3 times 4 times 5, that's my least common multiple, which is 60. Okay, so now what do I know? I know that k plus 1 must be equal to some multiple of 60, right? That k plus 1 must be equal to some multiple of 60, right? Where, of course, m is going to be a positive integer. Okay. So now we can really just check really quick, right? Does 7 divide 60 minus 1? And the answer to that is no. 7 does not divide 59. All right. Does 7 divide 120 minus 1? And the answer to that is yes. 7 does divide 119. So therefore, 119 is the smallest number of eggs that could have been in the basket. Okay. Now, this was the same solution. This was the same solution that we found when we did the Chinese remainder theorem. Okay. But with the Chinese remainder theorem, our solution was x is equal to, right, 119 mod 210. Okay, so we got 119 in both of these cases, but the Chinese remainder theorem provides for many an easier vision of all my possible answers, right? That maybe there was 119 eggs, but also maybe there was 329 eggs, right? Here, 119 works, but it may not be as intuitive for students to see, okay, well, what other possible values would work, right? 119 works, but what if it was more than 119, okay? Here, with the Chinese remainder solution, we would have the whole series of values, all the possible values, we would say, hey, that should be equivalent, that x is going to be 119 plus 210 times some integer, right, where n would simply be an integer. So that's the work on this divisibility and Brahmagupta's problem. There are different approaches, and like I said, here this approach might be more intuitive using divisibility for many students, but the limitation is that you don't necessarily see all the possible solutions, right? 119 is the least number of eggs that could have been in there, but what if there was more, right? So this has been Maths with El Profe Lo. Thank you for your time. Please reach out as you have questions.